Hi everyone. So we're moving on to chapter 5 of the notes after chapter 4, which was all that wonderful stuff about measurement observables, emission operators, commutators, etc., etc., etc. In this section of the module, we're actually going to start putting some of that quantum mechanics into practice. A couple of videos time, I will take you down the lab downstairs. We'll see a scanning tunneling microscope in action. We will make a measurement of tunneling current as a function of the separation between the tip and the sample, which defines our barrier width. You've looked at tunneling last year and from Newton to Einstein. Go back, revise those notes. I guess there's something like MRM 15 or MRM 16. Somewhere between MRM 8 and MRM 16 anyway, you will find the notes, all the notes in quantum mechanics, and the tunneling aspects are somewhere in there. Similarly, for those of you who did the Frontiers module, and I know not all of you did it, but for those of you who did, you also covered the scanning tunneling microscope in there. So you've seen the STM before. We're going to, as I say, go down the lab and actually see it in action and see real quantum mechanics happening before your very eyes. Before that, we need to put in place some groundwork. We need to, for one thing, think about what we mean by a current in quantum mechanics. Probability current or a flux of particles. And we're also going to have to think about scattering in the context of particles incident on steps and incident on barriers. Again, you've looked at this last year in from Newton to Einstein. We're going to tease out a few of the subtleties associated with particles that are incident on steps, changes of potential in terms of tunneling, in terms of whether they're transmitted or not, whether we get a flux of particles through different changes in potential, etc., etc. So let's start by thinking about flows of particles from a classical perspective. And then we'll introduce our quantum perspective. And we'll see there are very many parallels. So we have, let's say we've got a flow of particles. We have n particles per unit length. We'll just consider one dimension. Everything can be extended to 3 dimensions, but let's stick with what we've done throughout this module and keep to 1 dimension. Actually, next semester in the quantum world, you'll move into higher dimensions. So we've got n particles per unit length, moving at a velocity v. That means in a time interval delta t, that number of particles will pass a given point. Why is that? Well, think dimensionally. This is per unit length. This is, in terms of dimensions, and this is t. So we've got length. This is length to the -1. So this is a dimensions number, and that number is the number of particles crossing per that interval of time, which means the number of particles crossing a particular point or passing through a particular point at per unit time is that, which is simply that. So it's a simple expression. So let's call that, we conventionally use J for flux. So let's say J classical, J class is equal to that, which is this very simple expression. And if we have got, let's say, a flow of current of electrons, each with charge E, then our electrical current would be NVE. So we just have this times our charge. Now, this, of course, is an incredibly simplistic model because it assumes that the electrons just flow straight through, unperturbed, etc., etc., etc. But in terms of the overall concept, this is entirely valid, and we're also thinking one-dimensionally. So we've got number of particles per unit length times the velocity times the charge. That gives us our current. That's in the classic case. How do we map this across to the quantum mechanical case? Okay, so I'll put this up here. So J classical. That's our flux. So we're used throughout the quantum world module, and indeed last year, you're used to thinking of the wave function in the context of a particle, single particle. That's good. That's what you should do. And we'll be coming back to that very soon. But there is an alternative way of thinking about the wave function, and that's as a flux of particles. As something that can describe a flux of particles. Let's be careful here in terms of how I word this. What do I mean by that? Well, there are disadvantages, as we've seen, to thinking about a plane wave, thinking about a wave function in the context of a plane wave. So the bad thing is it's unnormalizable. The good thing is that it's associated with a single value of k, and therefore it's associated with a single value of velocity, because we know that p is equal to h bar k, de Broglie, and therefore our velocity is just that divided by our mass. So this is associated with a well-defined velocity. So if we're thinking about flux, that's already one part of our equation, in that we've got a well-defined velocity here. In terms of our particles per unit length, we can recast our wave function and think about the probability density. If we're casting this as a flux of particles, we can think of this, let me do it like this, which is the average number of particles per unit length. So we're just recasting that probability. Instead of thinking about a single particle, we're thinking about a flux of particles. And we're using a plane wave to describe a flux of particles. And this constant now tells us the average number of particles per unit length. Which means that, in terms of the quantum version of this, what we'll have is, let me get rid of this, J quantum is equal to, and this is for psi, I'll move it down here, so this is for psi x equal to a to the kx, so a plane wave is equal to that times h bar k over m, well that's our velocity. So average number of particles per unit length, velocity. Okay, so that's showing that classical quantum link and making sure that everything's consistent. Let's delve a little bit further into just what we mean by this flux, or what we also call probability current. And we do that pretty simple model. So we have some element which is delta xy. I've drawn it as two-dimensional, but it's only one-dimensional. And we've got probability of finding a particle in here, which is defined by this, where that, our probability density, is this. So probability density times our delta x gives us a number, gives us a probability. That you've all seen before. Now what we have is a current, a probability current in here. So let's say we have a flow of particles in, flow of particles out. And to use the same variable, we've got j, and we have j x t. So what exactly is this? This is a probability current. It's the net probability that a particle will pass, if we're defining this point as x, will pass this point x from left to right in a unit interval of time. Similarly, we have a probability current out the other side. This is defining the probability of a particle passing this point, and this is defining the probability of a particle passing this point, going from left to right. So, flow in, flow out. So, the probability of finding a particle in this region at time t plus delta t, and that's our probability density at that time, so that's our probability, is equal to, and I'm going to move this, is equal to, I'm going to move this down so you get everything on. So, is going to be whatever the probability was at time t, which is that, plus the probability associated with the incoming current at xt times delta t, because this is telling us the current per unit time, so we need to multiply that by delta t. And then that's coming in. Then we've also got to take the outgoing, which is going to be minus j at this point rather than this point, so that's x plus delta x t, and again times delta t. Okay, let's rearrange this. We're aiming for a differential equation, which is why I set it up, that relates the probability density to the probability current. So what we have is, so let's rearrange this. Px t plus delta t times delta x minus, let's bring this across, so we get a probability densities on one side, oh sorry, probabilities, is equal to, do a little bit of a rearrangement because we want to have our current at x plus delta x minus our current at x. So what we'll write that as we'll stick a minus sign out here, and then we're going to have j x plus delta x t delta t minus j, so it's minus jx t delta t. Okay. Now we're going to divide both sides of this through by delta x delta t. So what we're going to have, so let me try and make my writing slightly smaller. You see that? So we're going to divide through both sides by delta x delta t. So px t plus delta t, let me do all the steps, minus px t delta x divided through by delta x delta t is equal to minus j x plus delta x t delta t minus j x t delta t, and we're going to divide that through by delta x delta t. I will put the equation up as a GIF as well. So that goes, that goes, that goes. And on this side, that goes, that goes, that goes. So what we end up with, sorry, I just cleared the board. So what we have is px t plus delta t minus px t divided by delta t is equal to j, sorry, is equal to minus j x plus delta x t minus j x t. Right, now we consider this in the limit of delta t going to 0 and delta x going to 0. So what we end up with is, well, we end up with this. Or alternatively, we can write it as, obviously, as now this is a really important equation, not just in quantum mechanics. You've actually seen this, or if you haven't seen it, you'll see it very soon in classical fields. Basically the continuity equation. If we write that in a three-dimensional form, it might look a little bit more familiar to you. Where, remember this is a probability density, but we can write that as a density. It doesn't have to be a density in terms of probability density, just a density. So the amount of material, or the amount of a quantity, better way of putting it, the amount of a quantity per unit volume. plus, and that's going to be turned into a divergence, and this is going to be a vector. Okay, so this is the three-dimensional version of this. So where we've got the density of a quantity, the amount of a quantity per unit volume, and then the divergence, which is effectively the 3D analog of this one-dimensional gradient, of the flux. There's really, now this is, we've thought about flux in terms of particles, but you can also think in terms of flux in an electromagnetic sense, which you've looked at in classical fields. I'm just drawing these links just to show you that, again, we're not pulling something which is magically wow quantum out of the air. This links back to very, very grounded classical physics principles. Moreover, I'll not belabor this point, there's very strong links. There's actually one step of mathematics takes us from that equation to the diffusion equation we mentioned quite a while back. I mentioned this a little bit in the notes. You don't have to go into this in detail, but if you're interested and you like seeing the links between different aspects of physics, and that's really how you should think, don't think of this is my, try not to. I know the modular system forces you to think like this, but try to look for those links and try to get out of the habit of thinking, done this module, tick it off, forget it, move on. Done this module, tick it off, forget it, move on. Because the true beauty, the true elegance and true power of physics comes from seeing those links. And this is really, really elegant. We're thinking about quantum mechanics, but we can also map it back into universal equations spanning all of physics. Okay, so the more general version of this, you've got a sigma on this side. And that's describing the rate at which we create or remove this quantity, basically. What the quantity this density is describing. If we're not creating or removing, we've got an important conservation law. And then hence we set that to 0. And similarly here, we set that equal to 0, which means we're not creating or removing particles from the system. It's basically the conservation of mass. Once, in terms of our continuity equation for quantum mechanics. And this is our continuity equation more generally. Okay, I've cleared the board, put that up there. I've also written this down. This is our probability current, or flux, which we can get from this. I want you to do it. You will learn a great deal more from doing these steps yourself than from watching me do it. Think about this. It's actually not too difficult to go from here to here. You need to realize a couple of things. So first of all, that P is our probability density, which is okay. So what you're going to do when you differentiate this probability density with respect to T, you've obviously got a product there, so you're going to need to use the product rule for derivatives. And also in the notes, directly under equation 5.8, in that little check your understanding box, gives you a very useful expression in terms of two functions, f and g, and the derivatives of those functions, which will help you get from that expression via that to this. Try it. I've set it as a worksheet question. You learn a lot more if you work through those steps yourself than if I do it laboriously out line by line on the board. Again, as I said in the Don't Panic video, nothing more beyond really A-level mathematics is required of you here to do this and to do many other aspects of the problems we've been doing in the quantum world. One other thing to point out, which will become important later on, a couple of videos time, if that's our probability current, that's our current in terms of if we've got charged particles with a charge Q. We just take the probability current, multiply it by the charge, and that gives us effectively our electric current. And that's obviously important when we come to think about quantum devices, quantum electronic devices. The other thing to do is take a plane wave description and let's put the time dependence in explicitly. Plug it into this expression and make sure that everything's consistent. So that what we'll find is that our J, as we described it earlier, quantum, is equal to moving from that rather more sophisticated description of the probability current. Make sure that by plugging that in there, you get that. Okay, another question on the worksheet. Much better for you to do these things for yourself. Again, it's just differentiation. I will put the work solution up about a week, maybe 2 weeks after the problem sheet goes up. You know where you're aiming for. You're aiming to use that, plug it in there to get that. Make sure you can do it. Don't just rely on the solution coming online and going, oh yeah, I could have done that. Do it. And if you get stuck, that tells you that's very important for your learning. Rather than just going through it with the solution in this hand and going, oh yeah, I can do that. You need to have that confusion. You need to have that, stumbling blocks for your learning. Otherwise, you get a rather too rosy picture of your ability to do different questions if you've got the solutions sitting in front of you. So I'm not keeping the solutions back to be cruel, or just to be cruel. No, I'm not doing it to be cruel. I'm doing it to help you. I'm doing it to help you get on top of this stuff and see where the problems lie. One final thing before we close off this video on probability current and flux. Okay, so let's say instead of plane wave description, we've got a wave function that looks like this. So Gaussian-like, let's just write as e to the minus x squared, and times e to the I k0x. What that gives us is a wave function whose probability density looks like this. But actually, if we looked at, for example, the real part, because this is a plane wave, what we have is a Gaussian multiplied through by a plane wave. So what we'd have is this part is giving us our Gaussian. It's meant to be a Gaussian. I hope you see that. And then this is giving us our plane wave, which is going to be cos k 0x, I sin k 0x. So this thing will travel with its group velocity, which is defined by this wave vector, and is going to be Vg is h bar k0 over m. What do I mean by the group velocity? Well, it's basically the velocity of this peak. It's the velocity at which the peak of the wave packet moves, as opposed to the phase velocity, which is the rate at which these various ripples, if we take one of these ripples, it's the rate at which that moves. And as we've discussed back in chapter 3 and in, I don't know, video, I honestly can't remember the number of the video, but there's a whole video about group and phase velocity. There's a difference between group and phase velocity, but in this case, it makes a lot of sense to think about the current of particles being determined by the group velocity, the rate at which the wave packet moves as a unit. And so, in that case, for a wave function that looks like this, and that was our wave function defined at t equal to 0, then for a wave packet description, our probability current, nicely, would be, well, our constant times h bar k0 over m. And that is our group velocity. So rate at which the wave packet moves. And then if we wanted to know the current, if we've got a flow of these wave packets and they're each carrying a charge, thinking about electrons, then we just multiply this through by E, and that gives us our electric current, or electrical current, or electronic current. Okay, onwards and upwards. Next video about scattering in terms of a potential step. And we'll think about particles incident on that step, or flux of particles incident on that step. How many get transmitted, how many get reflected, and how does that depend on the energy of the particles compared to the height of the potential step. Okay, see you in the next video. Bye.